Hi, today is June 11th. My name is Yusuf Jivaji, and today we're going to be briefly going over the state space representation of a linear dynamic system. So what I'm writing down is what's known as the state space representation of a system. Let's briefly go over what each of these terms mean. This X is your state vector. This is a combination of all of the useful information that you care about of a system, like position, velocity, and that kind of stuff. This X is its rate of change, this X dot. X dot is equal to dx by dt. Okay. This is the matrix A that relates the current state of the system to its rate of change, and then similarly, this matrix B relates the the external force inputs to the rate of change of the system. Okay, so this is external. The second equation talks about the output of the system, but that's not going to be our focus for today. We're going to be focusing on this, the internal behavior of the system. Now, for example, let's say I have some wall, and attached to this wall is a spring and a damper, which are both connected to some mass, and which is on wheels, and it's able to move in the x direction. Or I'm going to call this 0. And it's got some initial position x naught and some initial velocity x dot naught. So I know that actually before that, I want to be able to observe what's happening to the position and to the velocity. So suppose that there's some arbitrary force f of t acting on the system. I can write the equation of motion as f of t is equal to m x dot dot plus the spring force, this is the damping force, plus the spring force that's acting on this mass. I can even rearrange this and write it as x double dot is equal to f of t over m minus cx dot over m minus kx over m. Okay, so this is great. And now I have an expression for this. Let's proceed. I'm going to write this. This is our rate of change vector. This is our vector x dot is equal to a function of the state vector. That's x dot, and it's also a function of the external forces that are happening as a result of this force that I'm applying. Okay, so I can see from here that this has this x dot term and this x term. So I'm just going to plug in the coefficients over here. Right, so I can see that negative k over m times x minus c over m times x dot is within this term over here. And I also have this 1 over m times f of t term. That's equal to this. Right? But what is x dot equal to? That's just equal to x dot, which is already part of the state vector. I can plug that in there. This is what is known as the state space model of this system. Right? And this is great. You'll notice that this is actually a first order differential equation as opposed to this second order differential equation. This is much easier to solve. In fact, I can write down the solution of this state space model as vector x of t is equal to the matrix exponential of at times x naught plus the integral from 0 to t of the matrix exponential of t minus s times a times b acting on f of s ds. This will literally give me an expression for the position and velocity of the system.